Welcome back to ECE 441A, 541A. Homework number 1, I have to keep reminding myself which class I'm in. Homework number 1 for this class is due Friday, and I think that's due at 11:59 p.m. Question? You may turn it in class, you may turn it in to my mailbox in the ECE building, or you can submit it to the Dropbox if you have a means of scanning it. Oh, D2L will be down, so Friday is maybe not the best time to be having that due, it sounds like. I think D2L, I think you're right. It does have routine maintenance scheduled from maybe 10 p.m. until 2 a.m. Friday to Saturday, so maybe try to get it in before the maintenance. If you miss the maintenance, that's okay. Just submit it at 2:01 a.m. or when you're just now getting started on the rest of your homework. Try not to stress too much. You can send me an email if you think that will make you feel better that I have it done at 11:59, but the D2L site was down. But thank you for reminding me. I usually don't have. Now I remembered why I didn't have things due on Friday evenings. You just reminded me. Today, what I want to do is start playing with all different kinds of representations of systems. We will begin with a transfer function, finding that from a block diagram. We'll start with a block diagram, and we'll find the transfer function associated with that block diagram. We will be typically specializing our attention to single input, single output systems, which allows us to divide things and not have to worry about taking matrix inverses with block diagram or with transfer functions. Then we will get into, with another example, a progression through the different representations. We will begin with a state space, and I may abbreviate that as SS. We will go to a block diagram, BD. From the block diagram, we will obtain a transfer function, and I'll illustrate a very basic form of Mason's gain, or Mason's gain is not too elaborate in the example that I've selected, but it extends to many more complicated scenarios. Then I hope you remember how to obtain differential equations from a transfer function. We'll do that. And I don't know, maybe we won't get into the governing equations of a DC motor. Maybe I'll just start going back and forth between different models, and this will be our model connection or representation connection lecture today. And Friday, we'll start playing with that DC motor. Let's begin. What we want to do, as I said before, we are dealing with single input, single output, and maybe you will see that abbreviated SISO, contrasting that with MIMO, multi-input, multi-output. We probably won't deal too much with MIMOs, but SISO, and this is now a single input, single output block diagram. And now let me see if I can space this properly. Let's say this is G1, and that could be a fourth order transfer function, G sub 1. It might be a system or a subsystem. Let's say we have another subsystem, G sub 2, and these are functions of S. I'm suppressing that, it looks like, in my sketch. And now we have these interconnected with some other blocks. Let's say we have an H sub 1 and an H sub 2. The output from G sub 2 will be our system's output. We'll call that Y. And going into G1 will be the output of a summing junction, and the summing junction's input will be R of S. And let's go ahead and take that R of S and also feed it all the way and have it more directly connected to G2, although it's indirectly connected if I put a line right there from G1. And H1, let's say, is a feedback element, which could also be some transfer function. It might be some sensor dynamics or another subsystem. And that's going back with negative feedback. H sub 2 is feeding back around the entire combinations. And there's our block diagram, which isn't too involved, but maybe you don't just instinctively know the transfer function description between R and Y in terms of all of these G's and H's. And what we want to do now in this discussion, it will be derive those using block diagram algebra, not Mason's game, but you can tonight see if you can get the same transfer function using Mason's game. What we are wanting to do here is find this transfer function, let's say T of S, that is the transfer function between the input R and the output Y. And the output goes on top, and the input goes in the bottom of that ratio. If we can find that ratio, then we have our transfer function T of S, which really says that we want, whatever we do in this block diagram, we would like to write our equations eventually in terms of Y of S and R of S, and then we can simply factor out the scaling polynomials that scale or weight Y of S and R of S, do the appropriate cross multiplications and divisions, and end up with our transfer function T of S. As I've said before, sometimes it's helpful to write your equations in terms of these outputs of the summing junctions, and a lot of times we sort of think of those as errors, so they may be denoted or symbolized by E's. Here I'll call E1 going into G1 and E2 going into G sub 2. Let's work our way backward from the output and see if we can eventually come up with just one equation that involves the output Y and the input R. Those are signals. To start, we can say that Y of S, and now you may want to be able to refer back to your diagram. I may have to slide back and forth a little bit, but that's now, in terms of that error signal, or that signal coming out of that second summing junction, that is simply Y is equal to G sub 2 of S times E sub 2. That shouldn't be too much of a stretch to keep track of. Now, what is E sub 2? E sub 2 is made up of a couple of signals. E sub 2 is the output of that second summing junction. It is made up of R, the input, and G1 of S times E1 of S. Both of those terms are signals. So E sub 2 of S is now R of S plus G sub 1 of S, E sub 1 of S. And I may drop the S. I may get lazy. Is that okay, the argument? But keep track of what's a signal and what's a system, because you can't be adding signals and systems. You have to be always combining like quantities or like entities. What's E1? E1, if we go counterclockwise, is R. And I'm probably, yeah, I'll go ahead and do that, is R minus H sub 2y minus H sub 1 G1 E1. And with these being scalar transfer functions, they commute. So H1, G1, I may write more alphabetically and just say G1, H1, the product of those. They're just ratios of polynomials in S, and those easily commute. So H1, G1 is the same as G1, H1. If we were dealing with multi-input, multi-output, we couldn't be doing that generically. Any questions so far? Now we have an equation with E1, R, and Y. We can get rid of the E1 by combining the terms. And we can divide through by that 1 plus G1 H1 on both sides, and we end up with E1 is equal to 1 over 1 plus G1 H1 times R minus H2 over 1 plus G1 H1 Y. And now what I want to do is actually use this in there for E1. And you can see how this is going to start getting a little bit messy in terms of expression. But now E1, is that where I wanted to do it? Actually, no. Where was my E2? I went one. I want to do this. And then I will have E2 in terms of R's and Y's. So let me now say E2 is equal to R plus, what G was it? It was G1, and now times that mess that I just had for an expression for E1. 1 over 1 plus G1 H1 R minus H2 over 1 plus G1 H1 Y. I'm almost home. I can now go back to my very first equation, and I have y is equal to G2 E2, and I now have found an expression for E2 in terms of just the inputs R's and the outputs Y. So that now I can say that y is equal to G sub 2 times that expression for E2, which is R plus G1 over 1 plus G1 H1 R minus G1 H2 over 1 plus G1 H1 Y. If I move that G2 through, and if I put everything over the same denominator, 1 plus G1 H1, then I can clean this up maybe a little bit, or start to form the ratio that I'm looking for. The first term is just G2 times R, but I want to get a common denominator. So I'm going to multiply that G2 by a special form of 1, which is 1 plus G1 H1 over 1 plus G1 H1, plus G1 G2 over 1 plus G1 H1 times R, plus G1 G2 H2 over 1 plus G1 H1 Y. And all of that's equal to Y. I missed a minus sign, didn't I? What else did I miss? Wake me up if I fall asleep. Okay? Might be embarrassing if I fall asleep, but fall over. Now what I want to do is multiply both sides through by 1 plus g1h1, and now I will simply have a polynomial equation. Now I have 1 plus g1h1 times y equaling, and I guess I can combine a lot of those pieces that are scaling r. I have g2 plus g1 g2 plus g1 g2 h1 r minus g1 g2 h2 y. Let me pull the y over to the left, and I now have 1 plus g1 h1 plus g1, g1 g2 h2 y equaling g2 plus g1 g2 plus g1 g2 h1 r. And now I can form the ratio that I was looking for, which is this ratio of y over r. So I divide both sides by r, and I divide both sides by what is scaling y, and I end up with my transfer function for that original block diagram being this collection of terms involving systems, G1, G2, H1, and H2. This is now my transfer function for that original system right there. And maybe some of you knew that by inspection. Did you just immediately write down that T of S in that form? That wasn't even funny, was it? But you can see, once you start learning Mason's gain, you will start to see why you might have a denominator expression that looks something like that. The G1, H1, the G1, G2, H2. But before we get there, are there questions on that? That was block diagram algebra. All you're doing is writing your equations maybe in terms of these outputs of summing junctions, and then trying to get rid of those signals in terms of your inputs and outputs to eventually end up with one equation that only involves input and output, and then you can take this ratio. Mason's gain will be worried about paths and loops and how these loops touch each other and how we combine these loops, pairs and triples and groups of 4, etc. Before we get there, let's now show ways of connecting, or just saying the connections between, what's SS? State space representation, BD, block diagram, TF, transfer function, and DE. Now you can text all the time, right? I need to convert an SS to a BD, to a TF and a DE. And that's a pretty quick text, isn't it? And you guys will know what you're talking about. Everybody else will go, are you talking code or what? No, just electrical engineering. Let's start with SS, the state space. And what we want to be comfortable with is any of these forms for our system representation, or the way that we've modeled that system. Suppose that we start with x dot equaling -1, 2, 0, -3, x plus 0, 1, u, and y is equal to 4, 5, x. The system matrix, A is square. What's the order of the system? 2. It's a second order system. Here is our input, and here is our output. For those of you that are comfortable with matrices, is this system stable? All right, let me ask another question. Do you know the eigenvalues of your system matrix? We'll learn all of this, but I'm just letting you know that it's all right there. It's just staring at us. That's an upper triangular matrix. And the eigenvalues are right on the diagonal in an upper or lower triangular matrix. Our eigenvalues are at -1 and -3. This is a continuous time system, which means that we want the eigenvalues to be in the left half plane to be stable. If we converted this into the frequency domain, we would have poles at -1 and -3 in our transfer function. And those are well placed in the S domain. They have negative real parts. And they would then represent, without doing any kind of control, in the open loop system, this would have modes that look like e to the -t and e to the -3t. And those are well behaved. If you kick it, it naturally wants to move in those with those modes. -1 and -2. So they really don't shake, they just decay, don't they? Those are exponential decays. E to the -t and e to the -3t. Which of those is the slowest mode? If you had to sketch e to the -t and then you sketched e to the -3t, which one would decay, take the longest to decay? That's the slowest mode. That's e to the -t, isn't it? That's the pole that's closest to the imaginary axis. I want you to start getting comfortable with those kinds of ideas and concepts, because we are going to want to take these ideas and maybe reorient or reorganize the poles in our system. Maybe they're not in the locations that we want. This is a state space representation. It's not the only one for this system. Now, can we create a block diagram from this system? And if we're talking about a block diagram, I'm looking for an all integrator. Block diagram, which means I'm in the time domain. How many integrators am I going to need for this system? 2. Where did that come from? It's second order. We have 2 states. We have 2 derivatives on the left. We have an x1 dot and we have an x2 dot. We would like to integrate those to find x1 of t and x2 of t. That's really what this block diagram, maybe what I could say, instead of an all integrator block diagram, I could say, show me an analog computer representation of this system. That was old school. When I was your age, we had analog computers, and we would hook up integrators, gain blocks, summing junctions, and we could simulate. Well, did the Wilbur and Wright have a name for their aircraft? I was going to say we simulated 767s, but that was way before then. But you could simulate a big airplane in the lab with just some electronics, with integrators, summing junctions, and gain blocks. Let's see what this looks like in terms of an all-integrator block diagram. You've just told me that we need 2 integrators And what are we going to do with those two integrators? Well, or how are we going to interconnect those with this system? The convention is simply to have the outputs of your integrators be your state variables. And then it makes the sketching of this block diagram very straightforward. We have two integrators, and we're going to have our states as outputs of the integrators. If you're looking for partial credit, what would you do? Well, I hope when you saw that A matrix, you would say, oh, that's second order. I know there's got to be two integrators. Give me some points. So you would sketch two integrators. You're on your way. Then the second thing is you go, let me label these. And now which way you label those might make your diagram a little uglier or cleaner, and you could just redo that. But let me make the one on the right, let me call that x1 of t. And the one on the left, I will call x sub 2 of t. Now here is some really intense calculus. What's the input to those integrators if the outputs are x1 and x2? x1 prime and x2 prime, the derivatives of those two signals. And here I don't know why I wanted to put a dot on there. Is that okay instead of a prime? I'm going to switch the notations up on you occasionally, but let's say we have x2 dot and x1 dot. And now we know what x1 dot is equal to from our state space representation. In terms of this representation, we know it's minus 1 times x1. So we go back here and we say, oh, x1 dot, I'm going to build that up. And from the state space representation, it's minus 1 times x1 and 2 times x sub 2. Is that clear where that came from? And then there's no input coming in to drive directly x1 dot. So I don't have to place an input into that summing junction directly. Using the same thinking process, x sub 2 dot is going to be what? What's x sub 2 dot? Simply minus 3 scaling x sub 2, isn't it? That's the only state that is making up x2 dot, but x2 dot also involves an input, u. It's plus 1, and that could be some other gain, so I'll just show you that you could put a gain in there, but in this case, it's benign, it's 1. Now, that's the dynamic behavior of our system. Everything that's happening dynamically in the system is represented in that piece of our block diagram. To find the output that we might measure, we now go back here and we say, oh, the y that we're actually measuring for this way that we've represented the system, we take 4 x1s and we add to that 5 x2s. And now we simply go here and we say, oh, we take 4 x1s and we combine that with, am I doing the right scalings, and 5 x2s. Which produces y of t. Questions on that all integrator block diagram? And that's an analog computer. If you had integrators, gains, and summing junctions, you could inject some electrical signal, U of t, that's representative of whatever it is that you're simulating in your analog computer, and produce the corresponding y of t, the output. If you put in a step for u, then what's going to happen to y? And this would solve that for you. This solves your differential equations. This is a way of, and you probably saw this in your math class, right? In your Diffie-Q? No? They didn't draw all integrator block diagrams? Probably not. But this gives you a good feel for what's going on, how these variables are interconnected. This is a time domain block diagram. Now, we've spoken before about GIFs in here. I don't know how giving I will be this semester, but if I was so kind as to say, give me the frequency domain block diagram for that system, could you do it? And what does it involve? Just change the integrators, erase those little squiggles, and replace those with 1 over s's. And then you have your frequency domain block diagram. And that's what we use to create our transfer function, which is the next step in our connection process. Questions on that? That's now our block diagram in the frequency domain, which is now begging the question, can we find the transfer function? And you could use block diagram algebra like we did at the beginning of this lecture. But now let's do it a different way. Let's use Mason's gain. Well, we could find that transfer function many different ways. We might be interested in a g of s, which is y of s over u of s. And we're going to find that with Mason's gain now, but we could have found that g of s, do you remember from our state space representation, what the formula was for that? We have our output matrix times Si minus A inverse B plus D. We could have done that algebraically. We have the A, we have the B, we have the C, and we have the D. And we could find our transfer function with this expression. So we can go from state space to transfer function directly with just doing the algebra in the matrix, doing the matrix algebra. Let's now do it graphically. Let's find g of s graphically from this frequency domain block diagram using Mason's gain. And Mason's gain is all about paths and loops. The paths are all of the ways that we can move from the input to the output without crossing over our path as we're going. I think you can see that there's a really easy direct path between the input and the output y. We can have, let me say my paths are yellow. So we can go right there. There's a path. That connects the input to the output. What is that path? Well, we just simply have to incorporate all of the different terms and multiply all of those terms together. We have a 1 over s, we have a 2, we have a 1 over s, and we have a 4. We have 2 times 4, 8, times 1 over s times 1 over s, or 1 over s squared. That path is then 8 over s squared. It's just 8 times 1 over s squared. That's path 1. So let's write that down. We said it's all about paths and loops. Let's keep track of this. P1, path 1 is 8 over s squared. Now, can I erase this? Good. Is there another way of moving from the input to the output without crossing over myself when I'm making that, tracing that path? I can go through the integrator, and then I can take a sharp detour left and go up through the 5, and that takes me immediately to y. Another path then is to go that way. And I don't cross over myself to get there between input point and the output. And what's that path? P2. As an expression. 5 over s. Any questions on paths? Pretty straightforward, but sometimes they're buried in there and they're hard to see. That's the problem or the difficulty with Mason's gain. Sometimes you go, I didn't see that path. Well, sorry. Minus 50. I don't know. All right. So these paths are important. Now we need to talk about loops. And loops, I think, are fairly intuitive. Those are just things that go around and touch themselves once. So now if we go back and erase that yellow, loops, here's a loop. That's pretty easy, isn't it? Here's a loop. We have 2 loops in this block diagram. And when you're doing these paths and loops, you can't go against the arrow. So don't go back against an arrow. If an arrow is going this way, which way? To your right, you can't go left. Is that clear? You cannot go against an arrow. In this first loop, we're starting at the output of the first summing junction, going through the integrator, coming back through that arrow and back to where we started, and keep track of the negative signs. Let's call that loop 1. Loop 1 is what? We just form all of the terms products. L1 is minus 3 over s. Not very hard, was it, in this case? What's loop 2? Minus 1 over s. Okay, it's, ooh, what happened to my 8? The bottom fell out. Maybe if I go back and forth, it'll come back. A little magic. Oh, now it's green bottom. Okay. Now that we have the loops, we can form a determinant for this configuration. And the determinant, you just kind of have to know the strategy for finding it. And I'm going to call that delta. That's 1. That's always there. 1 minus. Then we have the sum of all of the loops that we've identified. So in this case, it's simply L1 plus L2. 1 minus the loops. Here's where it gets fun. Plus the sum of pairwise products of non-touching loops. So the loops cannot share any points in common. That's non-touching. So here is now the sum of non-touching pairs of loops. Do we have any such pairs of loops that are non-touching in this block diagram? Yeah, those don't touch. So we have L1 times L2. So that's now the product of non-touching loops. So I should have said the product. How do I want to do that? Let me do it a different way. Let me write it out. You're going to go, why is pi in there? Well, Tharp was hungry, I guess. It's the sum of product pairs. I have a pair for lunch, so all I'm thinking about is food. But now you'll hopefully never forget pairs, okay? Maybe isn't spelled the same, but work with me. We now have pairs. What else are we going to do? Well, we just keep going and going. We alternate the sign. Now we have the sum of triple products that are non-touching. We don't even have 3 loops in this block diagram, so we can quit. But in general, then we add what? Now we have 4 loops, their product, if they're non-touching. And we have the sum of all of those. Do you get the idea? We just keep going. Then we look for groups of 5, groups of 6. But the only time we have to product those is when they're non-touching, and include those in here. And the signs alternate. So that just keeps going and going. So what's our determinant for this example? I'll do the hard part. 1. Now what do? We subtract the sum of the loops. Well, subtracting minus 3 over s gives me plus 3 over s. Subtracting minus 1 over s gives me 1 over s. And now, did I have non-touching loops? Yes, I had a pair of those, didn't I? And so I now have L1 times L2, which the 2 minus signs cancel. I had a plus the product of those two, so I now have plus 3 over s squared. Is that okay? And I can combine those two in the middle if I wanted to. That's now 1 plus 4 over s plus 3 over s squared. And I'm actually going to probably want to eventually have that as a ratio of polynomials. If I get a common denominator, whoops, I now have for a numerator s squared plus 4s plus 3. And that's my determinant. Oh, we're almost there. Now we need cofactors. If we have determinants, we need cofactors. So what are these cofactors? This is all Mason's game. A cofactor starts with the determinant, and it's nice to actually keep it in terms of what we began with. Whoops. All of the pieces, because some of those pieces may not be used. cofactor 1. Each path has a cofactor. How many paths do we have in this example? 2. So we're going to have 2 cofactors. We're going to have a cofactor for path 1. We'll call that delta sub 1. We're going to have a cofactor for path 2. We're going to call that delta sub 2. The cofactor for path 1 is you look at your determinant expression and you retain all of the terms in that determinant that are not removed when we eliminate path 1, or that are not broken. What was path 1? Path 1 went right through here, didn't it? So if we remove that yellow, and if you virtually erased that, would that disconnect any of these loops? Yeah. It'd break them all, wouldn't it? So what's left in our determinant expression if we remove everything that was disrupted by removing path 1? That was gone, that was gone, that was gone. What's our cofactor for path 1? 1. How about the cofactor for path 2? Path 2 was right here. If we remove that, so if you virtually erase that path 2, have you disconnected any of the loops? So if we go back to our determinant, and now I'll do this maybe in blue, we've disrupted loop 1, haven't we? And that was this 3 over s term, so we don't have that one. We keep the other one, don't we? The 1 over s. But this guy got eliminated because that was the product, and L1 was disconnected. What's the cofactor then for path 2? It's the ones that aren't touched by the blue highlights, which is now 1 plus 1 over s. Is that okay? And now we can write our, finally, oh, I was calling this g of s, wasn't I, before? Our transfer function, g of s, is in the numerator, you multiply your paths times your cofactors, and you take the sum of all of those. If you had 5 paths, you would find 5 cofactors, and you would sum those products, path times cofactor, divided by the determinant. And that will get your transfer function. G of s is now path 1. Path 1 was 8 over s squared. Delta 1 was 1. Path 2, 5 over s. Delta 2 was 1 plus 1 over s. All divided by the determinant, which was s squared plus 4s plus 3 over s squared. And I've written the numerator so that we can put everything over a common denominator, essentially. We have 8 over s squared plus, let's say, 5s over s squared plus 5 over s squared over s squared plus 4s plus 3 over s squared. And what's our transfer function? We can get rid of the denominators in the numerator and the denominator. They're common, and we have 5s plus 13 all divided by s squared plus 4s plus 3. Our transfer function then is 5s plus 13 over s squared plus 4s plus 3, and that's now our transfer function. Questions on that? Now that we have the transfer function, and you could get that with block diagram algebra, we want to do the DE. This is like falling off something that's easy to fall off of. A bicycle. Just be careful, wear a helmet. But the differential equation, how do we find that? Well, this is just y of s over u of s is equal to 5s plus 13 over s squared plus 4s plus 3. Can you find the differential equation associated with y and u? We'll just cross multiply. We now have s squared plus 4s plus 13 times y of s is equal to 5s plus 13 times u of s. Now can you take that into the time domain? Yes, I got carried away. I wanted to add another digit to that 3. Thank you. Now this goes into the time domain and says that we now have y double prime plus 4y prime plus 3y of t is equal to 5 u of t prime plus 13 u of t. There's our differential equation. And what have we done? We've gone, and now we could actually put this into a block diagram and start over again. State space, transfer function, block diagram, transfer function. And I want you to get comfortable with all of those different representations. They all can be related. We'll pick up with DC motors next time.